All right, so now we're going to start looking at the intersection possibilities between lines and planes and between lines and lines in both 2D and 3D. So we'll start with the intersections of lines and planes. These ones are a little bit more straightforward because there's not as many options. So it shouldn't be surprising that if we have a line and a plane, there's one solution possible. So if you were to take your pencil and drive it through a piece of paper, where the pencil goes through the paper, that would be like the point of intersection. So in this little plane diagram that we have right here, the line is coming out of the top of the page and then going down through the bottom. That's why the lines are dotted. So that would be one solution. If the line is actually on the plane, we say that there are infinite solutions. And we say that there are infinite solutions because every single point that is on that line represents a point of intersection on the plane. Thirdly, there's no solution if the line has a parallel property with the plane. So the line isn't actually on the plane. So in this case, that line will never, never, ever intersect the plane. So there's a few ways that we can figure that out, whether or not it is going to render a no solution scenario. All right, as per usual, let's go ahead and start looking at some examples. So in each case, determine if the line and plane intersect. If so, determine the solution. Okay, so in this plane right here, we know that we have 9x plus 13y minus 2z equals 29. I know that that's a plane right away because I see a z component. Here we have the parametric equations for our line. So basically, I have a representation of x, y, and z. I have x, y, and z in my plane equation. If there is a point of intersection, there has to be some parameter t that is going to satisfy this equation. So I'm going to substitute that in. So I have 9. I'm going to change the x to the parametric equation plus 13 times negative 5. So all I'm doing right now is replacing the variables with the parametric equations of the line. It has to equal 29. Now I'm going to expand. So we have 45 plus 18t minus 65 minus 65t minus 4 minus 6t equals 29. So I'm going to collect all my like terms and I get negative 53t minus 24 equals 29. Negative 53t equals 53. So that means t equals negative 1. So at that particular parameter, if we have t equal to negative 1, we have a point of intersection. So that point of intersection is going to be, so x is going to equal 5 plus 2 multiplied by negative 1. So that is going to be 5 minus 2 is 3. Y is going to be negative 5 minus 5 times negative 1. So y is 0. And then z is 2 plus 3 multiplied by negative 1. So that's negative 1. So that point of intersection, so POI, would be 3, 0, and negative 1. If you were to take that point and substitute it into the expression up top, you would find that it will also satisfy that equation. So that's the first scenario. So that's one solution. The next one we're going to look at is we have the plane x plus 3y minus 4z equals 10. And we have these parametric equations. Now you probably are like, well, why is she doing another one of these? I just want you to see what's going to happen for each situation. So I'm going to start off the same way. I'm substituting the parametric equations of the line into the scalar equation of the plane. Okay. Oops, that shouldn't be a plus. It should be a minus since it's minus 4z. So minus 4 multiplied by 1 plus 3t equals 10. So if you go through and you expand everything, you are going to end up with 4 plus 6t minus 21 plus 6t minus 4 minus 12t equals 10. So 4 minus 21 is negative 17 minus 4, so I get negative 21. We have 6t plus 6t is 12t, so I get negative 21 equals 10. So the t disappears. Does negative 21 equal 10? No, it doesn't. So therefore, the point is not in existence. Or a better way of writing this, instead of saying the point is not in existence, is to say there's no point of intersection. So there's no solution. There's no common point here. All right, now the third scenario is when there is infinite solutions. So when we look at that, this one here, I have to do one little step further. I need to create the parametric equations, but I'm going to go ahead and do that and substitute in at the same time. So I have 4. My x is negative 2 plus 3t minus y. So my y parametric is 4 plus t plus 11 multiplied by 1 minus t equals negative 1. So we have negative 8 plus 12t minus 4 minus t plus 11 minus 11. T equals negative 1. So negative 8 minus 4 is negative 12 minus 11 is negative 1. 12t subtract t is 11t minus 11t. So the t is completely gone. So we have negative 1 is equal to negative 1. So this means the line is on the plane. So therefore, we have infinite solutions. All right. Now I just want to flick back for a second. So here, when we are looking at the direction vector, it has to be parallel to the plane. So if that direction vector is parallel to the plane, we can check even before we do anything to see if the normal dotted with the direction vector is equal to 0. Because if it equals to 0, that means they're perpendicular. So that tells us right away that there is going to either be no solution, because it means that the line is parallel, or we could end up having infinite solutions as well if that line is on the plane. So that's just something to keep in mind. Okay, so now we're going to look at the intersection of lines in 2 space. So you guys are very much familiar with this. So same kind of thing we just did. If our lines have one solution, they cross each other, we get an answer. An infinite solution, so we have one line, then we have the exact same line. And then obviously, if there are no solutions, it means our lines are parallel. Let's pretend they're parallel. I'm not very good at drawing straight lines on this tablet. So how are we going to be able to recognize those situations? It's all about substitution or comparing direction vectors, so on and so forth. So here, classify each system as having 0, 1, or infinitely many solutions. Okay, so I look at this right away, and I'm like, wait a minute, 4, 6, negative 10, these look like they might be multiples. So if I multiply, or actually in this case, I might even divide everything by 2. So I'm going to divide by 2. That is going to give me 2x minus 3y equals negative 5. I'm going to divide this one by 3, so that's going to give me 2x minus 3y equals negative 5. Exact same equation. So this is infinite. They're the exact same line. Now, in the vector form of the equation, you have a couple of options. You could turn the vector form into a y equals mx plus b and work with it that way, or we can use our parametric equations. So if I look at it right now, I'm going to actually compare the direction vectors. So when we look at the direction vectors, I see that I have negative 6, 8, and I have 9, negative 12. Both of those direction vectors, they're multiples of each other. So right now I know that these lines are parallel or coincident, and I don't know which one it is right now. So what I'm going to do is I'm going to see if 1, 5 is on L2. Because if it's on L2, that means the lines are coincident and there's infinite solutions. If it's not on the line, it means they're two different lines that have the same slope, and therefore there is no solution. So whenever we're checking, we're going to use our parametrics. So I know 1, which is the x value, has to equal 2 plus 9t. And then we have 5 would equal 1 minus 12t. So I have negative 1 over 9 equals t. So here we are going to have 4 over negative 12, which equals t, which is not the same as negative 1 over 9. So therefore, there is no solution. Now, so nothing really new when we were talking about that, but now we're going to look at the intersection of lines in 3 space. So in 2 space, there's 3 possibilities, but in 3 space, or in 3D, there are 4 different possibilities. So obviously, there's one solution, so the lines are going to intersect at one point. So the direction vectors are different. So the direction vectors are not the same at all. In this case, there's infinitely many solutions, so the first part are different. I should finish my thought. The lines are coincident, intersect at infinitely many points, so it's the exact same line. So in this case, you'll recognize that it could be this situation if the direction vectors are the same, or multiples. When I say the same, I mean multiples. The lines are parallel and distinct. So again, in this case, the direction vectors are the same. Now the new type of lines that we have, these are called skew lines. So skew lines are lines that are not parallel and are not going to intersect. And we can only have these lines in 3D. In 2D, there's only 3 possibilities. So if you were to sort of have your pencil on your desk and then to hold another pencil above it, those lines are never ever going to touch each other, but they don't have to be parallel. They could be, but they don't have to be. So this new term you need to look at is skew. So in this case, the direction vectors, like when there's one point of intersection, they're not the same. So by looking at the direction vectors, you can limit the possibilities. So if they're the same, then we know that they're either parallel and distinct or they're coincident. If they are different, they're either skew or they have a point of intersection. So what does the math look like when we do that? Okay, so determine if these lines intersect. If they do, find the coordinates of the point. Okay, so what do you think we're going to be using? Whenever we've been finding any of these intersections, we're going to be finding the parametric equations, potentially, to see if they intersect. But first, always look at the direction vectors. So in this case, they're the same. So direction vectors are the same. Now it says find the coordinates of a point of intersection. If the direction vectors are the same, can there be a point of intersection? No, there can't. There could be a line of intersection, but not a point. So not a POI. That's all we have to do here, because that's all it's asking. Do they intersect? The answer is no, they're not going to intersect at a single point. Okay. It doesn't ask what kind of lines they are, so they might be parallel, they might be coincident. I don't quite know that yet, but it doesn't ask me that. Okay, so here's another example. So determine the point of intersection of the following line. So in this case, it's telling you that there's a point of intersection. So the process to figure this out, we're going to start by creating the parametric equations for both lines. So I'm going to start with the first one. So I have 7 plus 2s. Y is going to be 2 plus s. And z is going to be negative 6 minus 3s. I'm going to do the same thing for the second one. So I'm going to have x equals 3 plus t, y equals 9 plus 5t, and z is equal to 13 plus 5t. So I'm trying to find an intersection point, which means the x, the y, and the z have to be the same. So I'm going to choose 2 parametrics to work with, and just for ease, I'm going to start with x. So I'm going to set x equal to x. So I'm going to go over here and do this. So I'm going to have 7 plus 2s is equal to 3 plus t. So I have that parametric equation because this is coming from x equals x because it's a point of intersection. I'm also going to use y equals y. I'm only using two of them. I'm going to leave the z untouched because that's going to serve as my final check. So for the y, I have 2 plus s equals 9 plus 5t. So now I'm going to isolate. So at this point, I have two equations with two variables. You can set it up for elimination or you can use substitution. It's up to you. I notice that I have a single t right here, so I'm going to isolate for that t. So the 3 moves over, so I'm going to have 4 plus 2s is equal to t. So once I have this, I'm now going to go over here and I'm going to substitute that in. So I'm going to have 2 plus s equals 9 plus 5, but instead of writing t, I'm going to put 4 plus 2s. So 2 plus s is going to equal 9 plus 20 plus 10s. So when I isolate all of that, I'm going to have negative 27 equals 9s. So negative 3 is equal to s. So that gives me what s is. From there, I'm now going to take that s and figure out what t is. So I have 4 plus 2 multiplied by negative 3 equals 2t. So 4 plus negative 6, so I get negative 2 is equal to t. Now I got to see that this actually works. So that's where the z equations come into play. So I'm going to set z equal to z. So I have negative 6 minus 3s equals 13 plus 5t. So negative 6 minus 3 multiplied by negative 3 is going to equal 13 plus 5 multiplied by negative 2. So if this is actually a point of intersection, the left side has to equal the right side. So I have negative 6 plus 9 is 3, 13 minus 10 is 3. So there is a point of intersection. So my point of intersection, it doesn't matter if I use my line 1 parametric or my line 2 parametric equations, but I do know that x has to be 7 plus 2 multiplied by negative 3. So that is going to equal 1. I know y is going to be 2 plus s, which is negative 3. So that's negative 1. And I know that z is negative 6 minus 3 multiplied by negative 3. So z is equal to 3. So that means my POI is going to be at 1, negative 1, and 3. If you were to take that and check the red parametric equations, you get the exact same answer. Okay, so the last example for this is determine if the lines are skew. So really, the question that I just asked you and what I'm about to do, the math isn't going to look any different except for one part, which is going to distinguish between the two situations. So once again, the direction vectors are different. So I'm going to write my parametric equations. So I have x equals 5 plus s, y equals negative 4 plus 2s, and z equals negative 2 plus 3s. The second line, I have x equals 2 plus 2t. We have y equals negative t. And we have z equals 1 minus t. So once again, I am actually going to start off with setting the x's again. So that part, x equals x. So I have 5 plus s equals 2 plus 2t. So that means s is going to equal, when I move that over, we are going to have 2 minus 5 is negative 3 plus 2t. So that's s. Now I'm going to do the same thing with y. So y equals y. We have negative 4 plus 2s equals negative t. So So then I'm going to take the s and I'm going to substitute it over here. So I have negative 4 plus 2 multiplied by negative 3 plus 2t equals negative t. So negative 4 minus 6 plus 4t equals negative t. So negative 10 equals negative 5t. So 2 is equal to t. So then I'm going to plug that back in. So s is negative 3, excuse me, plus 2 multiplied by 2. So s is going to end up being 1. Excuse me for 1 second. So in order to see if it's going to have a point of intersection or if the lines are skew, we are going to check with the z's. So when we do this, we get negative 2 plus 3, that's 1. 1 subtract 2, it's negative 1. They're not exactly the same. So that means there's no point of intersection. So the lines have to be skew. So hopefully that makes sense. Lots of information there, but ultimately it's all about comparing parametric equations.